Good afternoon, everybody. Thanks for sticking with it. We're almost at the end of a fantastic conference. I wanted to start maybe with kind of my thoughts over the week. I was sitting in one of the talks yesterday, reading about the new Google AI ChatGPT competitor. And thinking, how freaking lucky am I to be here today in this industry, right? I think there's a tendency for us all to start arguing about whose qubit is better. And I think we should, take time to take a step back and think about, we really are creating the future here, right? And I think, that my overwhelming thought is, how lucky are we, right? So I'm going to talk to you about Equal One today. And maybe start with our thesis, right? So the foundational thesis of our company is that compute has always advanced with the advance of silicon, and quantum computing will be no different. So what do I mean by silicon in that statement? I mean Moore's Law. I mean the 70 years and trillions of dollars investment in the silicon industry. Time and time again, people have said silicon will not be able to do X. Whether X is smartphones, whether X is automotive radar, whatever X is, CMOS has continued and Moore's Law has continued. And it's our view that it will continue into quantum and will be the technology to deliver scalable real-world quantum. We're a different company as well. This is maybe the different quantum company. We like to ask why. Why do we need 4 data centers to integrate a quantum computer? A data center for the quantum computer, a data center for the cooling for the quantum computer, a data center to orchestrate between the quantum computer and the HPC data center. Why do we need that? Why do we need a nuclear reactor to power our quantum computer? Our answer is you don't. We are the Occam's razor of quantum computing. The simplest answer is the one that's going to win. And our vision, as you can see here, is a quantum computer that can integrate into today's infrastructure. And we believe we have line of sight to delivering that. We are behind the other technologies, but we're on a very different scalability trajectory. And I'll talk to you a little bit more about that as we go through the talk. So 3 sections, I guess. I want to, for those of you who maybe, silicon spin is one of the main technologies. I'll give a little bit of an overview in terms of where we're at and where that part of the quantum ecosystem sits. I'll give a little bit of a talk as to where we are today, and why it's now becoming very clear that this is the technology that's going to win in terms of scaling. And then finally, I'll talk a little bit about ourselves and what we're doing. So really, if the main thrust, I guess, of the industry right now is a race to a scalable and an affordable qubit platform. And my apologies to anybody whose platform isn't named up here. There are others. But I would say the main 5 are superconducting, trapped ion, neutral atom, photonic, and silicon spin. I like to classify the first 2 as quantum 1.0. We've made massive progress. We heard this week about IBM's new machine. Massive progress in proving that quantum is real. Similarly, with trapped ion, again, some fantastic science, some fantastic companies. But those companies are running out of steam in terms of being able to scale to the thousands, the hundreds of thousands, and ultimately the millions of qubits that we're going to need. Superconducting has challenges in that the qubits need to sit at millikelvin. You cannot integrate other electronics. A fundamental tenet of our company is that integration is going to win. The ability to put electronics alongside the qubits is what's going to enable quantum computing. You cannot do that at millikelvin. Trapped ion is a complex system. You've got lasers. Again, as we scale here to the thousands, it's going to be very challenging. Neutral atom is better. I think what the companies like Pascal and Atom have done, and I really think they've taken the initiative here, and they've done some fantastic work and demonstrations. But again, you've got external lasers, you've got big systems. To integrate these platforms is not easy, and massive challenges. So that leaves the final two, which is photonics and silicon spin. We heard PsiQuantum yesterday, again, Quandela. There's lots of fantastic photonic companies. Our view is that silicon photonics has not yet arrived. I'm in the industry 30 years. Silicon photonics has always been the next best thing. We've not gotten it for classical electronics, and there's massive challenges to get it for quantum. We heard yesterday from PsiQuantum, again, fantastic results, fantastic efforts, but the challenges in getting that monolithically are extreme. That leaves what we're doing, which is silicon spin. We're putting spin qubits on the same chip as all of our electronics. We're integrating and getting, basically putting error correction, detection, all of the pulsing, everything you need on one chip. And I'll talk a bit about that in a while. If we go back a little bit on the history of spin qubits, it really started with this Loss de Vincenzo paper, right? This proposal back in 1997, where they said, how can we, here's a proposal of how we can do a qubit with a quantum dot. And that started, I suppose, our part of the quantum ecosystem. And that started to build around quantum dots. Andrew Dirac, Dirac in Australia was the first to demonstrate this back in 2013 now, so 10 years ago. So this is not a new technology. Again, similar to a lot of the others, it's been decades in the making, decades of science from groups around the world. And it's now coming to fruition, and we're now in a position where we can say, well, why is 2023 now the time for spin qubits? We believe it's the time, and again, although we're behind the other technologies, our belief is that ourselves and the other spin qubit companies are going to drive the commercialization of quantum computing. So basically, again, coming back to integration being a key, quantum, what we call system-on-chip processors. So system-on-chip for the quantum industry is quite disruptive, but actually for the classical, it's how we got automotive radar, it's how we got AI accelerators. It's where you integrate as much as you can onto one chip. Our team has built some of the most fundamental system-on-chip classical electronics, from the first digital and RF chips that went into smartphones, the first time we integrated CMOS and power amplifiers, the first time we did edge AI accelerator chips. So the team we have has done this before, and we're going to do it again in quantum. So putting millions of spin qubits. Again, the thing about our qubit is it's essentially a transistor. So once we solve the basic addressability, coherence, quality, there are still major challenges. But once we do that, this is a very different trajectory than some of the other technologies. So what are the product breakthroughs? Measuring and controlling single electrons. Again, the timing, I suppose, for this is right in that we are now down to geometries that can form quantum dots to the scale that we can confine a single electron. That hasn't been happening before. That hasn't been ready. We have control voltages and noise levels that are now at the point where we can control single electron. We can get down to nanovolts of voltage control, attoamps of current control. And so the timing is now, and these things coalescing together is the thing that really unlocks this and makes this a reality. Because I think one of the things we get quite often is a little bit of, this is too good to be true, right? If we spent billions on these other technologies, is this really true? And I think for us, it's actually the convergence of a number of different things coming together, whether it be geometries or control. And as you'll hear, silicon-28, which I'll talk about in a second, which is purified silicon, all of those things coming together, making putting qubits, putting quantum processors on a standard silicon process a reality. So we've done 7 test chips. This is the only technology to scale. We're working with the largest semiconductor manufacturers in the globe to make their processes quantum ready. We're not there yet, but we're not that far off. We're closer than maybe a lot of people realize. And we think in the next number of years, silicon quantum computing will become one of the players, one of the leaders in terms of the divine technologies. So I mentioned what are the things that have sort of unlocked this and why can we do it. I mentioned the geometry of the transistor. So we're now down to less than 10 nanometers geometry in terms of what can be printed with EUV. That means we can make wells that can confine electrons. We have control circuitry that can get down to the nanovolts, hundreds of nanovolts, attoamps in terms of control, which is what you need for the electrons. The other question, I guess, is material and quality of material. And there's been another major breakthrough in the last number of years there, which is around purification of silicon and placing that on the top layer of the wafer. So in natural silicon, there is a mixture of 95% silicon-28 and 5% silicon-29. The silicon-29 causes a major decoherence. It's now been proven experimentally that if you put a layer of silicon-28 on top of that wafer, you can improve it by anywhere from 50x to 100x, which then makes it's still a standard silicon wafer that can go through the same process, but it's got this purified layer on top, which means that you get 50 to 100x improvement in the qubit. And all these things coming together means that now is the time for silicon spin qubits. In terms of error correction, we have quite a differentiated approach to error correction. And our view, again, is that without integration, real-time error correction is not going to be possible. So a lot of the discussions around error correction today is post-processing after the fact. We believe error correction needs to be right at the qubit array. And we have an approach where we look at AI to learn the errors in the qubits and in real time correct the qubits. And so again, integration is the thing that unlocks this. Having your error correction circuitry right at on the same chip as the qubits, and yes, right at cryo. We have 3 generations of cryoelectronics done, 10 million transistors. So this is not now a big deal. This is actually a solved problem. And what that enables, as I talked to at the start, is a form factor that can integrate into today's data centers. So rather than talking about having your quantum computer separate in a separate data center, we can integrate right into the same rack. And again, I think the conversation today is not thinking about all the things that we think about in standard processors, in-memory compute, moving data around. I mean, the idea that we could do a classical calculation in a computer here, send it to the building next door, have the quantum operation done there, and then sent back is, to me, rather ludicrous. So this needs to be very, very close if we're going to get the bandwidths and the data rates that are going to be needed for the algorithms that we're talking about. So we integrate standard parts. So we're using cryocoolers from MRI machines. We're integrating, standard vacuum pumps. We have 4 machines now that have been operating nonstop for 2 years in this form factor, which is why we believe now is the time to make this a reality. This is a picture of the current machine. Let me see if I can see the pointer here. No, it's not working on that. So on the left, this is the full machine completely integrated. No external cooling. This plugs into a standard socket. We could have one here. We probably will next year. That just plugs into your standard socket, 1.5 kilowatts, 1 meter by 0.5 meter by 0.4 meters. This in the middle is this is our chandelier, right? That's a 20-cent euro coin. We have 1 input, 1 output, and 1 control line in terms of what the IOs that are required. And you can see Vin, and this is up in San Carlos for anybody who wants to take a look. So we have 4 of these made. We believe, again, this is not just about the qubits. This is a system integration, a trade-off between power available, between temperature, between performance. You can't just focus on one part of this. This needs to be a system view of the problem. And here again is kind of what I alluded to at the start, which is the current view of how quantum computers will integrate into HPC. This is actually essentially taken from a city report that was put out in July, where you'll see that you've got massive power required for cooling. You've got massive facilities required for quantum. And that doesn't matter whether, the surprising thing is it doesn't matter actually whether it's superconducting, trapped ion, neutral atom, or photonic, as we heard yesterday. There's massive facilities going to be needed for these things. You then have orchestration between the classical and the quantum. Our view is, no, that's not how this is going to work. This needs to work where we integrate directly into the current compute fabric and integrate into the data centers. So just a bit about the company and where we're at. So we're headquartered in Ireland. We've got offices here in San Carlos, also in Romania, and in Sherbrooke. We're backed by VCs, Atlantic Bridge, Matterwave, and the European Innovation Council. As I mentioned, we have 7 test chips done. We're 5 years old. We've been very quiet until we're sure that this is going to work. We're working with the biggest fabs in the world to get their processes quantum ready, and there's a path to do that. And again, what that means is that we can deliver compact quantum servers that aren't data centers that can integrate into today's infrastructure. Thank you.
Thank you so much. Thank you. That was really very interesting. Can you just touch a bit on some of the competitive differences and kind of USPs between your company and your technology and some of the others in the field that are
some of the others in this field?
Who are working particularly within spin qubits.
Some of them are in the audience, so I need to be... look, I think... there's Intel, right? So Intel is going after this approach. And then there's probably 4 or 5 other companies that are taking this approach. I won't say anything about them. I think some of them are talking later, so they'll be able to speak for themselves. I guess from our perspective, I'll just talk about us. I think, as I mentioned earlier, our team has been involved in some of the most impactful products that have come out of the semiconductor industry. And we think combining disciplines, combining both commercial and product is what's going to be needed, right? I think we're still in a phase where there's a lot of academic science, and that is absolutely key here. And without the science, we're nowhere. But we also need to think about how we're going to commercialize this and how we're going to make it into a product. And I guess our team is kind of set up to do that also. So that's what I'll say about us. Great.
Reach out
Thank you.